has been a dangerous job, but proper clothing and equipment, effective training, and careful vigilance can significantly reduce the risks you face. Many foundry safety practices, such as wearing adequate protective clothing and equipment, are mostly matters of common sense. But other metal shop emergencies, such as bridging situations and furnace runouts, require specific technical knowledge to manage safely. This video module is the first of 4 modules which review both the common sense safety practices and provide the more in-depth information needed to deal with specific melt shop hazards. It's the goal of this video series to make all foundry men aware of the life-saving precautions that must always be taken whenever metal is melted. In this module, we'll look at one of the most common of all foundry hazards, molten metal splash, and its more serious form, furnace eruption or explosion. Many serious foundry accidents occur during furnace charging when foundry men come in close proximity to the molten bath. Splashes caused by dropping large pieces of scrap and by water-metal explosions pose a constant danger. Wet charge materials are a particularly serious safety hazard in all foundries. When molten metal comes in contact with any water, moisture, or liquid-bearing material, it instantaneously turns to steam, expanding to 1,600 times its original volume and producing a violent explosion. This occurs without warning, ejecting molten metal and possibly high-temperature solids out of the furnace, and puts workers, the furnace itself, and nearby plant and equipment at risk. Here you can see what happens when wet scrap hits molten metal. The violent and unpredictable nature of a water-metal explosion makes the wearing of safety clothing by melt shop workers absolutely imperative. Such clothing can prevent disfiguring and incapacitating burns as well as fatal burns. Molten metal need not be present in the furnace for a water-metal explosion to occur. Explosions also can occur if sealed drums or containers containing water or even moisture are charged to an empty but hot furnace. In this case, the force of the explosion will eject the newly charged material and quite likely damage the refractory lining as well. If a foundryman's first line of defense against death or injury is safe equipment and training that enables him to operate it properly under both routine and emergency conditions, his final line of defense is his safety clothing. Wearing the proper protective clothing can mean the difference between walking away from a foundry catastrophe or being killed or injured. There are 2 types of protective clothing worn in a foundry: primary and secondary protective clothing. Primary protective clothing is the gear which you wear over your secondary clothing when there is significant exposure to radiant heat, molten metal, splash, and flame. It is designed to give you the greatest protection. Primary protective gear should be worn during work activities like charging, tapping, pouring, and casting operations, or whenever you are in close proximity to molten metal. Primary protective clothing includes safety glasses, a face shield, hard hat, jacket, apron, gloves, leggings, spats, cape and sleeves, and can be made of aluminized glass fabrics, leather, special synthetic fabrics, or treated wool. Foundrymen working with or directly exposed to molten metal must wear primary protective clothing. Improper flammable clothing is the #1 cause of severe burns due to molten metal. For eye-face protection, safety glasses with side shields would be the minimum requirement. For molten metal exposure, a face shield is needed in addition to safety glasses. Your eye is extremely susceptible to injury, and protection is so easy to provide. For head protection from flying or falling objects, shocks or splashes, a hard hat should be worn. Visitors should also be made to wear hard hats and safety glasses at all times, regardless of their duration of stay or place of visit. When working near places where there is heat, heat-resistant, flame-retardant gloves should be worn. Cotton hand mill gloves are a minimum requirement. In working near molten metal, foundry gloves which extend above the wrists should be worn. For protection of the body, arms, and legs, aluminized glass outerwear has been recommended by many clothing suppliers for protection against radiant heat and molten metal splash. Aluminized glass outerwear, similar to that pictured here, will reflect about 90% of the radiant heat away from the body while shedding molten metal splash and sparks. Use leggings to cover your legs. Pourers or laceless safety boots are recommended for foot protection from molten substance exposures. They can be removed quickly in case of metal getting inside. Metatarsal guard shoes protect the top of the foot. If laced boots are worn, they should be covered with spats, especially near the top where there is danger of the molten metal entering. Secondary protective clothing is worn under primary protective clothing and in areas where there is less hazard. It is used to prevent ordinary clothing from igniting and burning. Flame-resistant coveralls would be an example of secondary protective clothing. While secondary clothing is not a ticket to complete safety, it will help to reduce burns significantly. In many cases, serious burns and fatalities have occurred because ordinary clothing caught fire from a small spark or splash, not because of burns caused directly by molten metal. Along with secondary protective clothing, you also should wear natural fiber outer clothing, undergarments, and socks. Some synthetic fabrics melt or catch fire, and this can increase the burn hazard. Safety clothing suppliers recommend the use of washable, fire-resistant undergarments. Where airborne hazards and noise pollution pose a threat, safety professionals also specify the use of respirators and hearing protection devices. Silica dust particles are considered a health hazard when inhaled over time, but protecting yourself against this hazard is easy. Dust respirators should be worn when removing and installing furnace linings or where dust is prevalent. Be sure to use the appropriate mask for a given situation. Most masks protect only against certain types of dust and vapor. Certainly, foundries are hot places to work, and protective clothing adds to the problem of heat-related stress. But this protective clothing can save your life. While wearing protective clothing and equipment is the most important step you can take as an individual to protect yourself from metal splash, there are two other factors in protecting yourself from molten metal splash. These are distance and protective barriers. Distance is a very straightforward form of protection. The further away you are from the furnace or molten metal, the safer you are from metal splash. That's why furnace manufacturers promote features such as automatic charging systems and computer control. These systems enable people working with the furnace to stay further away and still do their jobs. In all situations, people not directly involved in working with the furnace should stay out of the immediate area of the furnace, especially during charging, melting, and pouring operations. Protective barriers can provide shelter from molten metal splash and heat when distance is impractical. An example of a barrier would be a screen around a pouring control station on the melt deck. Since many serious foundry accidents occurred during furnace charging, when foundry men come in close proximity to the molten bath, remote charging systems serve to enhance safety by permitting the operator to be safely back from the furnace or behind protective screens during charging. Typical charging systems include belt and vibratory conveyors, charge buckets, and chutes. Charging systems also reduce damage to furnace linings caused by heavy charged material striking the lining. In foundries where most of the charge originates as scrap, wet charged materials pose the greatest cause for concern. Some foundries reduce the possibility of water-metal explosions by storing scrap under cover for at least 1 day and then carefully inspecting bales and containers for any residual moisture. But a more reliable solution being used by an increasing number of foundries today is to use both remote charging systems and charge dryers or preheaters. Dryers and preheaters make an important contribution to safety by minimizing surface water and moisture. This is accomplished by passing scrap through an oil or gas-fueled flame tunnel before the scrap enters the bath. This greatly reduces the chance of metal-water explosions. These systems also burn off much of the dirt and oil, producing a cleaner charge and reducing the energy required in the furnace to melt the scrap. Cold charge, or tools, and easily fragmented materials pose a special hazard for induction furnaces and their operating personnel because they may contain a thin layer of surface or absorbed moisture. On contact with the melt, the moisture turns to steam, causing spitting or splashing. Proper protective clothing and face and eye protection will normally protect the operator. Preheating the charge and tools prevents many splashing injuries. In ferrous metal foundries, the greatest splashing risk occurs toward the end of the melt, when a foundryman adds ferroalloys or introduces tools into the melt. Ferroalloy materials can absorb moisture from their surroundings. Sampling spoons and slag rakes collect moisture as a thin film of condensation. Following manufacturer's instructions for storing alloying materials and preheating tools minimizes moisture accumulation, reducing the risks of splashing. In a non-ferrous foundry, spitting or splashing can accompany the introduction of ingots into the melt, as surface condensation comes in contact with molten metal. Ideally, ingots should only be placed in an empty furnace or on top of solid foundry returns. Ingots added to a molten pool should be preheated or introduced using a remote charging system. The combined use of drying and preheating systems and remote charging systems can significantly reduce accidents related to furnace charging operations. In summary, foundries can provide maximum safety from molten metal splash by preheating or drying charged materials before they are put into the furnace, by using remote charging systems, by providing protective barriers or screens for melt deck workers, by keeping anyone not involved in the melting operations a safe distance away from the furnace, by providing safety clothing and personal protective equipment to workers and visitors and requiring that it be worn. As a foundry worker, you can assure yourself the greatest protection from metal splash by wearing the proper primary and secondary safety clothing and personal protective equipment. You must never lose sight of the fact that working with molten metal in a foundry is serious business and involves many hazards, ranging from minor burns to fatal burns. But by being aware of the dangers and taking the appropriate steps to safeguard yourself, you can reduce the day-to-day risks associated with your work. Furnace charging is a dangerous job, requiring both careful vigilance and the protection afforded by proper safety clothing and equipment. It involves the hazards of metal splash and possible furnace eruption if wet or damp materials get into the furnace. But there is another potentially more serious danger associated with melting a charge in an induction furnace. It's called bridging. A bridging condition exists when cold charged material in the top portion of the furnace is not in contact with the molten metal in the bottom of the furnace. When bridging occurs, cold charged material is no longer serving to moderate the temperature of the bath during the melting cycle. Also, the air gap between the molten metal and the bridge acts as an insulator. The molten metal in the bottom of the furnace, under the impact of full melting power, will superheat. This superheating in an induction furnace will occur very rapidly and will soon raise the temperature of the bath above the maximum temperature rating of the refractory. Also, excessive stirring in the bottom of the furnace, due to the small metal mass and high power density, will combine with the high metal temperatures to cause rapid lining erosion or possibly complete refractory failure. Without immediate attention to a bridging condition, a runout may occur. A runout can cause a fire under the furnace and in the pit area, with loss of hydraulics, control power, and water cooling. It also can cause an explosion if the molten metal encounters water in the pit or if it burns through the coil. Bridging can occur in any induction furnace, and all furnace operators must be able to recognize bridging and its dangers. All operators also must know how to solve a bridging problem. Bridging may reveal itself with one of several warning signs. The most common and clear warning sign that bridging has occurred is that the melt is taking longer than calculated. If the charge is not melting down into the furnace as expected, or if there is solid metal in the top of the furnace when the operator would normally expect the bath to be fully molten, the operator must switch off power immediately. Under no circumstance should the operator increase power or extend melting time to try and melt that metal. If ferrous metal is being melted, the chemical reaction which it creates on contact with the furnace lining will, under superheated conditions, produce carbon monoxide. This gas may reveal itself as small blue flames on or in the bridge. The appearance of these flames indicates the bridge may be pressurized and it must not be breached. In the case of a non-ferrous charge, gas production will also occur, but there are no flames or other visible indications of its presence. If a bridge occurs, power must be turned off immediately until the bath temperature is known. If the bridge has completely sealed the top of the furnace, pressure may build up between the molten metal and the bridge. If this has happened, it's safest to allow the molten metal to freeze. If it can be determined that the bridge has not sealed the top of the furnace and that pressure has not built up within the furnace may be tilted to attempt to melt out the bridge. Put a ladle in front of the furnace to catch any metal that may spill out. Then tilt the furnace carefully until the molten metal is in contact with the bridge material, approximately 45 degrees. The molten metal will then melt a hole in the bridge. Power must be off while melting out the bridge. All unnecessary personnel should be kept away from the furnace while melting out a bridge. Do not stand in front of the furnace. Under no circumstances should an oxygen lance or burning bar be used to cut through the bridge. After a hole has been melted through the bridge, return the furnace to the upright position. Then, check the temperature to make sure the molten metal is not superheated. Begin adding charge through the hole in the bridge to raise the bath level. This brings the molten metal into contact with the bridge, melting it into the bath. Adding charge also will cool the molten metal, and power may have to be reapplied to maintain the proper pouring temperature. However, power must not be turned on if there has been a ground leak detector trip indicating metal to coil penetration, if the variable frequency power supply had been running at a higher than normal frequency, or if the fixed frequency power supply required more than the normal number of capacitors to be switched in, indicating an eroded lining, if there is excessive surface lag visible, evidence of serious lining damage, or if the water temperature in the coil is higher than normal. Each of these conditions indicates that molten metal may be next to the coil and requires an immediate evacuation of the area until the metal in the furnace has completely solidified. If none of these conditions exists, the melt can continue. Once the bridge has been melted away, the furnace should be poured empty as soon as possible so the lining can be examined for any signs of damage. If there is any doubt about the integrity of the lining, replace it. The chance of a bridging situation occurring can be minimized by using proper charge material and by making sure that different sizes of charge material are added correctly. It is vital that every furnace operator be able to recognize and react correctly to a bridging situation in his furnace. His life and the lives of his co-workers may depend on it. Proper and well-maintained refractory linings are absolutely crucial for the safe operation of all induction furnaces. Your life depends on that furnace lining standing as a firm and reliable barrier between you and the molten metal inside the furnace. This requires that you treat the lining carefully during all furnace operations, as well as follow comprehensive inspection, record keeping, and replacement procedures. Without question, metal runout ranks among the most severe accidents that can occur during melting and holding operations. Runouts occur when molten metal breaks through the furnace lining. If cooling, electric, hydraulic, or control lines become damaged, there may be an imminent danger of a fire or water metal explosion. Maintaining the integrity of your furnace lining is the key to preventing a runout. And the key safety system to alert you to the possibility of imminent lining failure is your ground leak detector. This system, necessary in most non-removable crucible furnaces, includes both a ground detector circuit associated with the power supply and a ground leak detector probe located in the furnace floor. It is designed to provide both warning of metal-to-coil penetration of the refractory lining, a highly dangerous condition that could lead to a furnace eruption or explosion, and important protection against electrical shock. The probe in the furnace is composed of an electrical ground connected to several wires which extend through the refractory and contact the molten bath or a conductive crucible. This system serves to electrically ground the molten metal bath. In some small furnaces with non-conductive, non-removable crucibles, where the bath cannot be practically grounded, the ground leak detector probe may take the form of a wire cage located between the crucible and coil. This wire cage serves to ground the bath if metal penetrates through the crucible. Both of these probe configurations provide shock protection to melt deck workers by assuring that there is no voltage potential in the molten bath. If molten metal were to touch the coil, the ground leak detector probe would conduct current from the coil to ground. This would be detected by the ground detector module, and the power would be shut off to stop any coil arcing. As a normal safety precaution, power to the furnace always should be turned off during slagging, sampling, and measuring. To keep the ground leak detector probe working properly in a furnace with a rammed lining, care must be taken when installing the lining to ensure that the ground leak detector probe wires come into contact with the bottom of the lining form. Also, when patching a furnace lining, it is essential that the ground leak detector probe wires remain exposed, permitting contact with the furnace bath. It is important to check your furnace's ground leak detector probe frequently, because it can be covered during improper furnace relining, can burn off, can be isolated by slag, or otherwise can be prevented from providing a sound electrical ground circuit. But the goal of all safe induction operations is not to have a refractory lining fail while in service. When furnace linings fail, it's usually for one of these reasons. The wrong refractory material was used for a particular application. The refractory was inadequately or improperly installed. The normal lining wear produced by the inductive stirring of the metal was not monitored, and the lining was allowed to become too thin. Physical shocks or mechanical stress damaged the lining. Excessive temperatures or thermal shocks damaged the lining. And finally, slag or dross was allowed to build up. Any one of these situations can result in a metal runout from an induction furnace. Let's look at each in more detail. Choosing the right refractory material for your specific melting or holding application is the first step in preventing a furnace runout. The best way to select the right refractory is through close consultation with your refractory supplier. Proper installation of the lining is as important to the safe operation of the furnace as the selection of the right material for your application. Again, follow the installation recommendations of your refractory supplier. It also is especially critical that you exactly follow the refractory manufacturer's procedures for drying and sintering, and never hurry this project. In induction furnaces, refractory linings and crucibles are subject to normal erosion due largely to the inductive stirring caused by the induction furnace's magnetic field. In theory, refractory wear should be uniform, but in practice the most intense wear occurs at the slag metal interface, where sidewalls join the base, and at thin spots caused by poor lining procedures. The entire furnace should be visually inspected whenever it is emptied. Special attention should be paid to these high wear areas, and observations should be accurately logged. Eroded or damaged linings must be repaired or replaced immediately. Although useful, visual inspections are not always possible, nor can visual inspection alone reveal all potential wear problems. Some critical wear areas, such as the lining forming the inductor box of channel furnaces, remain covered with molten metal between relinings. The presence of a low-density refractory area can likewise escape notice during visual inspections. These limitations make lining wear monitoring programs essential. In situations where frequent visual inspections of coreless furnaces are not practical, when, for example, they are used for continuous holding and dispensing, operators should remain alert for two important warning signs of lining wear: attainment of maximum power at a lower than normal applied voltage, or higher than normal operating frequency in variable frequency power supplies, and in fixed frequency units, an increase in the number of capacitors needed to be switched into the circuit to maintain unity power factor. Useful though they may be, changes in electrical characteristics must never be thought of or used as a substitute for physical measurements of the lining itself. The sudden or cumulative effects of physical shocks and mechanical stress can also lead to a failure of refractory material. Bulky charged material dropped into an empty furnace can easily cause the lining to crack upon impact. Remotely controlled automated charging systems are engineered to put charged materials into the furnace without damaging its lining. Refractory manufacturers take furnace temperature extremes into account in formulating their products. For this reason, it is important that refractory materials be used only in applications that match a product's specified temperature range. Slag or dross is an unavoidable byproduct of melting metal. Chemical reactions between the slag or dross and the melt increase the rate at which the lining erodes. Remember, your furnace's refractory lining is all that stands between you and the molten metal in your furnace. Select it carefully, install it properly, treat it with care, inspect it frequently, keep careful logs, and remove it immediately when it is worn out or damaged. Your life and that of your coworkers may depend on how well you install and maintain every lining. Before leaving this safety topic, let's look at the protection afforded by spill pits and the hazard of refractory dust. It's important to be prepared to deal with a furnace runout should one occur. That's why no induction melting furnace should be operated without adequate, carefully maintained, and dry spill pits. These pits, often called runout pits, are located under and in front of induction furnaces. They serve to contain safely any molten metal spilled from the furnace as a result of accident, runout, or dumping of the furnace in an emergency. Without adequate pits, spilled molten metal would flow across the foundry floor, endangering workers and damaging furnaces, other equipment, and structures. This free-flowing spilled metal also could produce devastating fires and explosions. Spill pits must be kept completely dry at all times. This requires careful vigilance since these pits are low points and easily catch water from leaks, cleaning operations, or ground seepage. Wet pits are bombs waiting to explode. If molten metal comes into contact with water in the pit, it is likely to produce a bomb-like blast, with molten metal flying everywhere. Furnaces must not be operated if their spill pits are wet. Long-term exposure to high levels of refractory dust may pose a health hazard to foundry workers. The best way to protect yourself from this hazard is to wear the proper dust respirator whenever you are exposed to refractory dust. This is particularly true when you are installing a lining in a furnace or removing a worn lining. Induction furnaces equipped with lining push-out systems speed the lining removal process, lessen the risk of damage to the coil, and reduce worker exposure to refractory dust. Maintain a safe furnace lining. Have a dry and clean spill pit ready for emergencies, and protect yourself from the hazard of refractory dust. These are basic practices in maintaining a safe foundry working environment. While many electrical systems in foundries are similar to those in other industries, a foundry's induction melting system involves high levels of electrical power, levels more commonly associated with power company substations. For this reason, induction systems require special attention to electrical safety. Induction systems with their open-air bus bars and other exposed conductive surfaces present more electrical hazards than most other types of industrial equipment. Consequently, modern induction furnaces and power supplies are designed with safety systems to reduce these hazards. For example, in the latest induction installations, current handling bus bars and components are covered by protective enclosures. To provide additional protection, there are several types of safety interlocks designed to turn off power if power supply access panels or doors are opened. But for these and other safety systems to be truly effective, all workers must respect the protection these systems provide and not override or defeat their functions. The following are some basic rules for electrical safety in the melt shop. The first rule is that only trained induction system operators should be permitted to run induction melting equipment. A trained operator must be fully knowledgeable about the system's controls, alarms and limits, diagnostic functions, and safety features. He must be fully versed in the safety rules and procedures related to the system's operation. To keep all personnel alert to the dangers associated with induction electrical systems, warning notices must be posted on all equipment that operates at high voltages, and these notices must not be removed or covered. All power supply doors and lockable protective enclosures must be kept locked and the keys secured and controlled. Unless an induction system operator is also a trained electrical service technician, he should never open the power supply cabinet doors or be allowed access to any secured high voltage areas. Next, induction melting equipment should not be run if any safety systems are inoperable, such as the ground leak detector or probe, door interlock switches or locks, or capacitor pressure switches. Finally, power supplies must be turned off whenever any process involving worker contact with the metal bath is taking place, such as taking samples, checking metal temperature, or slagging. This is to prevent shock or electrocution if the metal bath were to come into conductive contact with the induction coil. In addition to the safety interlocks designed to turn off power automatically when power cabinet service access doors are opened, modern induction melting equipment normally includes a variety of other key safety systems. Ground leak detection systems turn off power if metal in the furnace comes close to or touches the induction coil. This serves both to help prevent a runout and to reduce the chance of shock or electrocution from power conducted through the bath. Ultra-fast acting solid-state circuit breakers on larger systems and current-limiting reactors and quick-acting circuit breakers on smaller systems provide protection against component failure and major line disturbances. Secondary isolation from the incoming power utility line may be provided through an isolation transformer located between the inverter and the furnace. Primary isolation may be provided by locating a transformer between the incoming power line and the inverter. Capacitor pressure switches detect capacitor malfunctions that can lead to pressure buildup inside the capacitor case. If undetected, this pressure buildup may cause capacitors to explode. Pressure switches help prevent this by shutting down the power supply if pressure builds up. In many advanced induction power systems, self-diagnostic controls not only prevent the unit from operating when a fault is detected, but also identify the location of the fault. In servicing induction equipment, supervisors need to be especially aware of electrical safety. It is imperative that they impress on even their most experienced maintenance workers that shortcuts, such as overriding safety interlocks, are totally and completely unacceptable when working with even the smallest induction furnaces and power supplies. The following procedures will help minimize the risk of electrical accidents while servicing induction furnace coils, power supplies, and conductors. First and most important, allow only fully qualified and properly trained personnel to perform maintenance or repair on any induction equipment. And before any maintenance or repair work is done, ensure that the equipment is disconnected and locked out. A safety lockout system is an effective measure to prevent electrical shock. It is the safest way to prevent power from being turned on accidentally while equipment is being serviced. With this system, the individual performing the service work uses a lock to secure the circuit breaker in the off position. He or she then keeps the only key until the service work is complete and the equipment is ready to be restored to operation. At that time, the same individual who put on the lock removes it, allowing the breaker to be closed and power to be turned on. Remember, forbid entry into any enclosures until the main circuit breaker is locked in the off position and breaker poles are confirmed to be open. Even then, wait 5 minutes after opening a breaker before opening cabinet doors. This allows capacitors time to discharge harmlessly. Next, test all bus bars for residual voltage before touching anything. Be aware that there are some areas inside the power supply that are on the incoming side of the breaker and remain energized even after the breaker is off. In newer units, these are marked and protected by individual covers. If you remove such a cover, you must replace it after the area has been serviced. This will help protect the next person servicing the unit from accidental contact with the energized component. If the power supply energizes more than one furnace, leads to the furnace undergoing maintenance or repair must be disconnected from both ends of the coil and the furnace induction coil grounded. Typically, induction furnaces require two separate electrical systems. One for the operating system, such as the cooling system, furnace tilting, and instrumentation, and the other for the induction coil power. Electricity for the induction coils normally is furnished by a specially designed power supply connected to a three-phase, high-voltage, high-amperage utility line. This means that foundry workers cannot assume that the power to the furnace coil has stopped just because service has been interrupted to the furnace's cooling system or hydraulic pumps. In foundries, as in many other manufacturing operations, moving equipment poses a trapping hazard to the unwary. Trapping occurs when all or part of a worker's body becomes caught between moving equipment and another object or structure. Trapping hazards on the melt deck may include moving charge buckets carried by overhead cranes, traversing or pivoting charge conveyors, belt conveyors, moving ladles, and tilting furnaces. Induction furnaces tilt forward to pour, then return to the upright position for charging and melting. While in motion, they can pose special hazards for foundrymen. One preventable accident occurs if a foundryman's feet become trapped between a descending furnace top plate and the working platform. Ideally, a foundryman should know the path a furnace or other piece of mobile equipment will travel when it is set into motion, and remain behind designated safety barriers until the machine completes its duty cycle and returns to its normal resting position. Trapping also is a hazard during maintenance operations when workers must be within a piece of equipment's motion path. That's why special steps must be taken to disable the equipment electrically by locking out the power and securing the equipment mechanically before maintenance work begins. In a foundry, this is particularly true of furnaces. If work is to be performed on a tilted furnace, for example pushing out a lining, the furnace must be secured in the upright position with a mechanical support. Reliance on hydraulics alone could lead to the furnace dropping without warning, causing injury or death to anyone trapped underneath. Working with molten metal always has and always will be a dangerous occupation. Responsible foundrymen acknowledge the risks and the possibility of serious accidents. While it is impossible to remove the risk from melting metal, it is possible to make the melt shop an accident-free workplace. Your life and that of your co-workers could depend on your attention to safety rules and procedures and on knowing what to do in emergency situations.